Okay, so this class will keep looking at continuous random variables. And so the thing that we're going to be looking at is archetypes of continuous random variables. So what I mean by archetypes are specific examples. So these are important specific examples. So what we saw last time? So the example that we saw is that x is uniformly distributed in AB, and this meant that the density function for x is f of x, which is equal to 1 over b minus a. If so, this is evaluated at x. If x is in AB, and this is 0 otherwise. Okay, so one of the things that we need to remember in general is that, so here is what is the probability of getting uniformly a random number between a and b. It's going to be the density function associated with this. It's just going to be 1 over the size of the interval indicated over the set of the interval. So in particular, the probability that my random variable x is in a set A is going to be the integral over A of f of x dx. Okay, so this is just the integral of 1 over b minus a times the size of A over this thing. So this is what we saw last class. So the point I wanted to make here is that to be able to say what is the uniform distribution x over an interval AB where A and B are the parameters, we only need to identify its distribution function. This is its density function. So there is 1-to-1 correspondence of density functions and random variables and continuous random variables. So what do I mean is a continuous random variable is completely determined by its density function. So in the case of the uniform distribution between an interval, this is the density function associated to this. And then what we're going to keep seeing today is other types of continuous random variables in which we specify what is the density function. Okay, so we can write a definition or an example. So x is said to have distribution, a normal distribution with parameters 0 and 1. So this is what it's called mu, and this is what it's called sigma squared. X is normal distributed, so it's x has standard Gaussian distribution. X has standard Gaussian distribution which means, so this is what this means. X is n distributed like n0, 1. X has standard Gaussian distribution, and this is the same that the density function f of x at a given x is equal to e to the minus x squared over 2 over square root of 2 pi. Okay, and this is for every x in R. Okay, so if we plot this function, this is an exponential with a super thin tail. Then it goes like this. And it keeps going like that. Okay, so this is a Gaussian, which, I mean, my picture perhaps is not the best, but this is symmetric around the origin. And the change of concavity to convexity has to do with the parameter 1. Okay, so the sign where this change from being concave to being convex, I think has exactly to do with the distance 1. Okay, so first, one of the things that we should check from this thing is that this is a density function. So what do we need? What do we need to check that f of x is a density function? Okay, so one of them is that f of x is positive for every x in R, which this is always positive. So an exponential of a number is always positive, divided by square root of 2 pi is positive. And the other thing that we need is that the integral from minus infinity to infinity of f of x dx is equal to 1. Okay, so this is the probability of x in R. Okay, which is just equal to 1. So you actually have to have that the integral of this whole density function is equal to 1. So how do we calculate that? How do we actually realize that this has that this is the right normalization constant? So why is this the right normalization constant? Okay, and this is a little bit of a funny integral, which you have to go to 2D to make it 1D. So how do people do this thing? So let's say that we take the integral. So we want to calculate the integral from minus infinity to infinity of e to the minus x squared over 2 dx. Okay. So this is the question. What is this equal to? And the trick here is to take the square of this. So you take the square e to the minus x squared over 2 dx. And now we take a square of this. Now the square of this is just the multiplication of this times another one of this, but we can change the name of the dummy variable. Okay, so here this is equal, and this is changing the name of the dummy variable. So here I called it x, but I could have called it y, z, or whatever I want. So in particular, I can take that this is equal to the integral from minus infinity to infinity e to the minus x squared over 2 dx times the integral from minus infinity to infinity of e to the minus y squared over 2 dy. Okay, But the multiplications of two integrals that have different dummy variables can be written as the double integral of the product, e to the minus, let's call it x squared plus y squared over 2 dx dy. Okay, but what happens here is that this can be written, this is a 2D integral that depends on the radius. Okay, so here, if we put this in polar coordinates, so in polar coordinates, this is the integral from 0 to infinity of the integral of r, so of 2 pi times r times e to the minus r squared over 2 dr. Depends only on the radius. Okay, so now we make the substitution. U is equal to r squared over 2. And what you get here is that this is the integral from 0 to infinity, so the 2 pi is outside. The integral from 0 to infinity of here we would actually flip, so here we would have e to the minus u with a minus sign outside, so let's just simplify the minus sign outside, and then we would care, so basically we get minus 2 pi integral from 0 to infinity of e to the minus u e to the minus u du, which in this case this is just equal to 2 pi. Did I get this right? So we had 2r squared over 2, and here, yeah, there is a minus sign probably that is wrong. You can figure that one out. The point I wanted to make is that if you do these polar coordinates, you get that the squared of this number is equal to 2 pi, which implies that the integral from minus infinity to infinity of e to the minus x squared over 2 dx is equal to the square root of 2 pi. Okay, so in particular, this makes you check that the density function, the integral over the whole set, is equal to 1. Okay, so more in general, we say x is distributed, normally distributed with parameters mu and sigma squared if f of x at x is just given by 1 over the square root of 2 pi sigma squared times e to the minus x minus mu squared over 2 sigma squared. Okay, so, and if we do the same picture as we did before, here we would have mu okay, this doesn't look that symmetric, but it should be symmetric around mu, and this change of concavity to convexity would be at sigma. Yeah, would be at sigma. So the point is, these are two parameters, and this is what is called the mean, and this is what is called the variance. So why is this called the mean and the variance? So let's look at the expected value of x. So one of the things is you can transform from one distribution to the other. So let's first realize the following. So what is the expected value? So let's say that x is normally distributed with normally a standard normal distribution. Okay, so this is standard, which means mu is equal to 0 and sigma squared is equal to 1. Okay, so this is the standard choice. And so in this case, what is the expected value of x? The expected value of x for one we saw last class is the integral from minus infinity to infinity of x times e to the minus x squared over 2 over square root of 2 pi. But this integral is equal to 0 because of symmetry. Okay, so the probability of, if we look at the picture, which again is not that symmetric, so the probability of being right of 0 and being left of 0 is the same, and the probability that being in this interval or being in this interval is the same. So this mirror symmetry can be seen in this integral, in which if we switch x by minus x, we get the same answer. Okay, so if we flip minus infinity and infinity, we get the same, and plus infinity, we get the same thing. So the expectation of this thing, the integral of this antisymmetric function is equal to 0. Okay, so this is antisymmetric. Okay, so if you have the integral of an antisymmetric function, you get 0. Okay, and now the next thing that you can see is that if x, and this one might be a little bit more of an exercise for you, if x is distributed with a parameter mu and variance sigma squared, then let's call it y, which is equal to x minus mu over sigma, is distributed as a standard Gaussian. Okay, so if you have something that is normally distributed with parameter mu and variance sigma squared, you can actually take this to obtain a new distribution which has which is standardly distributed. So if we want to see what is the probability that x is less or equal than a, this is the same. So here we can remake this transformation and saying that x is equal to sigma y plus mu. So this is the same as the probability that sigma y plus mu is less or equal than a, and this is just the same as the probability that y is less or equal than a minus mu over sigma, which is just the integral 1 over square root of 2 pi of the integral from minus infinity to a minus mu over sigma of e to the minus x squared over 2 dx. Okay, so the point of this just quick computation is to make you realize that if you want to calculate something for a normal distribution which is not standard, you can still do it in terms of the standard distribution just by changing appropriately with the parameters. Okay, so what is the sort of, I mean, and let's do the computation for the variance. So usually the way that you do this is that these integrals are usually tabulated. That is to say, computed to a high degree of accuracy. Okay, so in terms of motivations of why we want to look at the Gaussian for a process, the idea is that the Gaussian is what results after taking a bunch of averages. Okay, so the Gaussian distribution arises out of taking the average of identically distributed processes. Okay, so even if we just take, even if xi is distributed, identically distributed processes that are independent. So if we take xi, which is Bernoulli with parameter p, then what we're going to have is that 1 over n, the sum from I equals to 1 up to, let's say, capital N of xi minus p will converge to a normal distribution with is centered as 0 and has variance p times 1 minus p. Okay, and this thing here is the central limit theorem. Okay, so if you want to calculate on average how many heads you're going to get after n tosses, this is with n going to infinity, then you are going to approximately get n times p heads, but up to second order, it's going to be a Gaussian distributed with average 0, and the variance is going to be p times 1 minus p. Okay, and this is something I won't do right now, but this is an exercise for you. So the exercise is that if x is a normal distributed with mu and sigma squared, then the expectation of x is equal to mu, and the variance of x is equal to sigma squared. Okay, so this is just calculating the integrals and figuring out what it comes out. Okay, so what other distribution it has? This is a really important one, and this is something you should definitely know. We'll make even more emphasis on this distribution when we get to the central limit theorem. So what's another distribution is the exponential. The exponential distribution, which would say that x is distributed with exponential parameter lambda. So this is really similar to the discrete one, in which f of x at x is just e to the minus lambda x over lambda. Okay, so this is the continuous version of the discrete one. Okay, and similarly, we need to check fx is density function. So this is clearly positive, and the integral from minus infinity to infinity. And sorry, this distribution function is for, this is when x is positive, and it's 0 otherwise. Okay, so this is the case that x is positive. Okay, x only takes values, the capital X only takes values of little x positive. Okay, it doesn't take negative values. So if you take the integral from minus infinity to infinity of f of x little x dx, it's actually equal to the integral from 0 to infinity. This has to be equal to 1. The integral from 0 to infinity of e to the minus lambda x over lambda dx, which is just equal to 1. Okay. Okay, so this is the exponential distribution. So it's something, so again, we can calculate the expectation of this. So what is the expectation of x? It's going to be the integral from minus infinity to infinity of the integral from 0 to infinity of x e to the minus lambda x over lambda, and yeah, here to be able to do this, you have to do the same computations as before, and then you can end up figuring out that this has to be equal to lambda. Okay, so I guess a way of doing this is by considering this guy and writing it as lambda x to the I over I factorial, and then multiplying by x. So in a sense, what you get here is that this is the derivative. This would be the derivative with respect to lambda of this thing, and you can take the derivative outside as we did for the discrete variable, and actually take, so the derivative here is like the derivative over lambda of this function here. You integrate by parts the derivative with respect to lambda, and you can actually show this thing here. Okay, so this was a little confusing, but the point is, so if you want to prove this, is look at the discrete case. Okay. What is the other distribution that we're going to do or use in general is the gamma distribution. So the gamma distribution is x is distributed gamma with parameters lambda and t. So these are parameters. So it has two parameters, and this is capital gamma. Okay, so here we have the density f of x, which is equal to 1 over gamma of t times lambda to the t, x to the t minus 1 times e to the minus lambda x for x positive and 0 otherwise. Okay, and so where does this distribution gamma come out? First of all, I should tell you what gamma of t is. Gamma of t is the gamma function. So gamma of t is the integral from 0 to infinity of x to the t minus 1 times e to the minus x dx. Okay, and what you can see is that for this particular function, you can realize that this gamma of t is exactly what you need to normalize this distribution. Okay, so this is what it's making, that if you take the integral, this definition of gamma of t implies that the integral from minus infinity to infinity of f of x is equal to 1. Okay, and so this distribution can be interpreted as the time of the tth. Okay, so the number t success when each of the trials is distributed with exponential distribution. Okay, so this might be a little odd at the beginning, but what is the idea? So the distribution can be the time of the tth success when each of the trials is distributed with exponential distribution. So the point is you run a process of an exponential distribution until you get the first hit, and then you start another process with exponential distribution until you get the next hit, and then you sum them up, and that would be gamma lambda 2. Okay, so in general, this exponential distribution is related to perhaps the decay of radioactive materials, and so this is telling you when this exponential distribution is telling you when is the material going to decay. Okay, and the probability that it's going to decay is higher at the beginning than for longer things. Now, if you start asking not for the first decay, but for the tth decay, so when it has decayed t times, so first it should have decayed once with this distribution, then decay another time with this distribution, and so on. So if you look at what was the time that it took the material to decay t times, this is going to be distributed by this function gamma with parameters lambda and t. Okay, so in particular, did I get this wrong? Yes. So I thought, yeah, I was getting this wrong, of course. So here the lambda goes up. Sorry about that. So in particular, if gamma of lambda 1 is exactly distributed, so if you put t equals to 1, this is 0. This gamma of t is just the integral of this, which is equal to 1. And this gamma to the t, lambda to the t is lambda to the 1. So gamma of lambda 1 is just equal, it's just distributed with exponential and parameter lambda. And if we have x1, x2, which are exponentials with parameter lambda, then what is the time in which the radioactive material has decayed twice? It's going to be x1 plus x2, which is distributed with gamma lambda 2. Okay, and then this parameter t doesn't need to be an integer, but can actually be any continuum between between 0 and infinity. Okay. Yeah, this gamma distribution, exponential distribution, they will come up in examples and they will make sense in the particular examples, but I wanted to try to make them clear of where they come up for. Okay, so here you could actually just check as well that this is the right normalization constant to actually get that this has integral 1, and this is because this thing has a change of variables. The change of variables lambda times x actually has the right homogeneity for you to be able to pass it into the function itself. Okay. What can we see from this relationship? Actually, what we can see is that we expect that the expectation of x is going to be t over lambda, because if we have the expectation, yeah, that's what I would say, the expectation of this guy is 1 over lambda. Okay, that would be hard to prove if it was wrong. Anyway, so the expectation of a gamma distribution will actually be t over lambda. These computations become a little involved and they're actually not that interesting, so I'm not going to actually do them. But anyways, for you to know, you can actually compute these things. Okay, then the last distribution that we're going to check today is the Cauchy distribution. So the Cauchy distribution is just, so let's say x is distributed with Cauchy if the density f of x is equal to 1 over pi of 1 plus x squared. Okay, and this is for every x in R. So what is special about this distribution? So this distribution is what is called fat tail. Okay, so this has what they call fat tail. So the previous distributions that we were seeing before all have an exponential decaying tail. So it's something that goes to 0 fast. This guy has a fat tail. It has such a fat tail, so the remark is that the tail is so fat we cannot define the expected value. So the expected value is the integral from minus infinity to infinity of x times the density function, which in this case would be pi 1 plus x squared. But this is not absolutely convergent. Okay, so you would expect the expected value of the Cauchy random variable is just 0 because of symmetry, but the tail is actually so fat that this thing is not absolutely convergent. So you cannot actually claim that the expectation is 0 because it's not well defined. So we cannot define the expected value. Okay, in this case you could make sense of it, but you have a problem with the tail being too fat. Okay, so let's keep going a bit more and let's look at the, these are the type of examples that we are going to be looking at. I don't think I did a great job, but I think we'll keep looking at them as they appear. So let's look at the dependence. of continuous random variables. So we had talked about independence, but what happens with dependence? So the idea is that we can actually, the random variables can be like so correlated that they can be like sort of a multiple of each other in the specific settings that we're going to look at. So let's look at the distribution function. So one of the things that we had looked before, so let's say x is a random variable. Then f of x, which is the distribution function, is equal to the probability that x is less or equal than little x. This is just the distribution function, and it has density minus infinity to x of f of x dx. Okay, so this is the density function. Okay, so for two random variables, x comma y, we can have the joint distribution function, which is f of x y of little x and little y is equal to the probability of x less or equal than x and y less or equal than y. Okay, so one of the things I should say first, this can be easily generalized for more than two. For more than two variables. Okay, so you can just take n variables and do the same. So a criterion, so let's call it a proposition or lemma. Yeah, it's not even a lemma. Let's call it an observation. So x comma y are independent if and only if the joint distribution f of x, y, x, comma, y is just the product of the distribution f of x, x times f of y, y for every x, comma, y. Now, okay, so this is a way of checking independence. So these guys are independent, so this just depends on the probability of x less or equal than x and y less or equal than y. And if they are independent, this is just the probability that x is less or equal than x times the probability that y is less or equal than y, which is exactly equal to this side. Okay. So now I reintroduced the joint distribution function because we say that so let's do a definition. x and y are jointly continuous if there exists a function f(x,y) from R2 to 0 infinity such that f of x, y of little x and little y is the integral from minus infinity to x of the integral from minus infinity to y of the joint density of x, y, and let's call it st ds dt. Okay, so f of x, y is the joint density of x, y. Okay, so in particular, you can, for instance, uses of the joint density function. So let's say that we want to calculate what is the probability that x plus y is bigger or equal than 4. This is going to be a union over the values of x. So what is the probability of this? You can do it by doing the same things that we were doing before. So this is going to be the integral over, but not over the whole space, but over the space of sets x plus little, so s plus t is bigger or equal than 4 of the joint density of x and y, which is f of x, y at st ds dt. Okay, so in particular, so this set can be written as the integral from minus infinity to infinity of the integral from 4 minus s to plus infinity of f of x, y s t ds dt. Okay, so you first integrate from 4 minus s to plus infinity, which are all the possible values for y, and then you integrate from minus infinity to infinity. Okay, and what you can see by the things that we did before is that basically any set, the probability, so the thing that you should realize is that the probability that x, y, and now this is a vector, this is a 2 vector, is in a set A, which is contained in R2, is the double integral over A of the density function ds dt. Okay, so what am I trying to say is the following. If you want to know, so let's say that we have a set A here, and now this is x, this is y. So what is the probability that x, the vector x, y lands in A is going to be the integral over A of the density function. But this is the joint density function. So this is a generalization for a 2 vector of we had seen for a 1 vector. Okay, so you can do this for the case x plus y bigger or equal than 4. So in the case that A is equal to x plus y bigger or equal than 4, the integral is given in, so if this is 4, this is 4, this is a set A, and the set A can then be written as the integrals over S over these lines, like this, or we can have flipped the integral signs and integrated it like this, or you can integrate it over lines like this, whatever you want. Okay, so this is similar to what things we have done for joint distribution functions for discrete variables. For continuum variables, you can get the same things as before, like we can obtain from the joint distribution, we can obtain the marginal from the joint distribution or density, we can obtain the marginal density or distribution. So what do I mean by this? Okay, so let's say that we have f of x, y. So if we have access to f of x, y, how do we obtain f of x or f of y? Okay, and how's the idea of this? So for this marginal thing, so okay, let's try to write it in its full thing. So let's say that we have the probability that x is less or equal than x. The probability that x is less or equal than x is equal to the probability of x is less or equal than x intersection y is in R. So this just means that y is less than plus infinity. So, but then this is the integral from minus infinity to x of the integral from minus infinity to infinity of the joint density function f of y, x, y, s, t, ds, dt. Okay? But then what this implies is that here, in this thing here, so first let's integrate dt and then ds. So this thing here is equal to the f of x at s. Okay? So the marginal distribution, okay? So if we integrate out one of the variables, we obtain the density function for x. Okay? So if we integrate out one of the variables, we obtain the density function. We obtain the density function for the other random variable. Okay, so just to write it in clean, f of x at x is equal to the integral from minus infinity to infinity of the joint distribution f of x, y at x, comma y integrated in y. Okay, so morally, if you look at the picture here, if you want the marginal distribution for x at a point x here, you have to integrate the joint distribution over this whole line. Okay, so okay, and this is what it's called. So in this case, this thing here, this thing here is the first marginal of f of xy. The second marginal is the same but integrated against the x, and it's the density function for f of y. Okay, so this is similar to what we did for discrete variables, similar. For discrete variables, let's have the theorem. So let's say that x and y are jointly continuous, and g going from R2 to R is continuous, then the expectation of the random variable, which is given by g of x, y, is just the double integral from minus infinity to infinity of g of little x, little y, of the joint distribution f of x, y, x comma y, dx, dy. Okay, so this we did for discrete random variables, and the proof would be the same for continuous random variables. Now, instead of having a sum in the discrete random variable case, you would have an integral in this case. So let's consider now as an example. So let's do an example. Where x and y, so we have random variables x comma y, such that their joint distribution f of x, y at little x and little y is 1 over 2 pi times the square root of 1 minus p squared of the exponential of minus x squared minus y squared plus 2px times y over two times 1 minus p squared. Okay, so the idea is that this parameter p is measuring correlations between x and y. Okay, so let's look at the marginals. So let's look at marginals. So what is the first marginal? So the first marginal, okay, so let's look at the first marginal. So in this case, the density function for x at x is equal to the integral from minus infinity to infinity of 1 over 2 pi square root of 1 minus p squared times e to the minus x squared minus y squared plus 2px times y over 2 times 1 minus p squared dy. Okay, so now the idea would be to take out the things in the integral that don't quite that we don't need, and so what we would do is that this is, so now what we want to see is that this guy is actually a standard Gaussian. So then what I would like to take out is e to the minus x squared over 2 divided by 2 pi square root of 1 minus p squared. But now if I take e to the minus x squared over 2 outside, I need to add the piece that is missing here. Okay, so then this would be the integral from minus infinity to infinity of, so if here I have taken this over 2, so I mean, this thing here I have minus x squared over 2 times 1 minus p squared, and then I add x squared over 2, and I subtract the x squared over 2, which is here, which is, this is equal to x squared of 1 minus 1 minus p squared over 2 times 1 p squared. So what I get here is e to the minus, so this one goes with this one and you get a plus p squared, so minus p squared x squared minus y squared plus 2p x times y over 2 times 1 minus p squared. Okay, so the reason why I did this is because we want to complete the square. Okay, so if we want to complete the square, this is just e to the minus x squared over 2 divided by 2 pi square root of 1 minus p squared. And here, if I complete the square, I just get the integral from minus infinity to infinity. So this is a dy integral, e to the minus x, so let's call it y, minus p times x squared over 2 times 1 minus p squared dy. Okay, and this guy is the distributed like a normal distribution with mean p of x and variance. Okay, so all of this here is n of p of x with variance 1 minus p squared. Okay, so all of this integral is just equal, with a square root of pi. So here would be a square root of 2 pi, and there will be another square root of 2 pi outside. So if you do this integral, you actually get that this is equal to 1. And so then you get that the first marginal is just e to the minus x squared over 2 over square root of 2 pi, which is just normally distributed, standard normally distributed. Okay, so similarly, a couple more pages. similarly, y, so the marginal f of y at y, which is the integral from minus infinity to infinity of f of x y, little x, little y, d of x, is just going to be e to the minus y squared over 2 over square root of 2 pi, which is just distributed normal 0, 1. Okay, so all right, what is this example trying to make you realize? Is that this p parameter here, which we haven't set, so it clearly has to be between 0 and 1, so p is between minus 1 and 1 for this to make sense, and this should be even a little open. Yeah, let's put it close just in case. So the idea is that even though the distributions are fixed on the endpoints, okay, so the distribution of x and y do not depend on the parameter p. Okay, so you can have the random variables that are distributed in which their joint distribution depends a lot in what is the correlation between them. Okay, so there is a special case which is p is equal to 0. And so in this case, in the special case, p is equal to 0. So then what we get is that the joint distribution f of x y is equal to 1 over 2 pi e to the minus x squared minus y squared over 2. But this is equal to 1 over the square root of 2 pi, and I'm going to write it in a weird way, e to the minus x squared over 2 times 1 over square root of 2 pi e to the minus y squared over 2, like this. Okay, and this thing is the marginal of f of x at x times, so this is at x, y, the marginal at y, the second marginal at y. Okay, so, and this is another way, this thing here, this equality here, this is another way of checking this is another way of checking independence. Okay, so when p is equal to 0, x and y are independent. Okay, I think I'll stop today with this thing, and then next class I will look a bit more at the covariance and some inequalities that you can do with this, with the covariance and these kind of things. So the point is that just for you to know further along of what we're doing, the covariance of x and y in this specific example is going to be equal to p. And so the point is, when p is equal to 1, what we had is that x and y are completely determined. So if p is equal to 1, what you can check is that y is equal to x. Okay? So, and if p is equal to minus y, then what we have is that minus x is equal to y. Okay, so p equals to 0 is the case in which they are independent, and then p is equal to 1 is when they are actually completely dependent. Okay, so the value of 1 completely determines the value of the other one. So, okay, so this is similar to what we had done for discrete variables, but in continuum variables everything is analogous.